Swayam Prabha. Digital India. Educated India.
Welcome to Module 6, Lecture 27 on testing of mechanical and electrochemical properties of the surface. In this talk, I will be particularly discuss about different mechanical testings, and then subsequently in part 2 we will discuss about mechanical remaining part of the mechanical testing as well as the electrochemical testing of the surface of any component. So, if you talk about the mechanical properties, then certainly you have to focus on those properties which are dependent on the surface, particularly when we talk about the surface dependent mechanical properties. Those are hardness or micro hardness, then wear and also fatigue property. So, now if you just quickly go through the ways by which you can evaluate those properties, certainly none of them can be evaluated by non-destructive testing as we discussed in the last class. So, you have to go for destructive testing, and in most of the cases you have to follow the simulated conditions of those particular degradations or properties where the component needs to be used, but usually we just use a few standard evaluation protocol which is near similar to that of you can say that simulated conditions, because actually if you would like to measure those properties in simulated condition, you have to basically have the specific environment and specific equipment where you have to do the testing. Now, if you talk about the hardness, certainly hardness is the material properties which is not much dependent on the environment unless and until it basically there is a surface film formation because of the interaction of the component with environment, or maybe because of the component's interaction with the mechanical load which is there in the environment. But otherwise hardness is more or less you can say that materials properties which depends on the microstructure and composition of the component. So, if you talk about that hardness, it is nothing but we evaluate these properties by measuring the resistance to the indentation of the component. So, if there is any indentation, in this particular case what you do, you basically indent the surface with a indenter, and resistance to indentation is measured as a measure of hardness. So, there are different ways by which you can measure the hardness of any component, and particularly now if you just think of the hardness measurement, certainly you will find that in different scales you can measure the hardness. So, if you talk about the macro scale, you will just simply say as hardness. Similarly, if you go to micro scale, you call it as micro hardness. If you go to nano scale, you call it as nano hardness. So, we will discuss about the different hardness measurement units which are applied for measurement of hardness and their details. So, this is the typical hardness measurement which is called Brinell hardness testing, and where that ASTM specification is ASTM E10 standard. So, in this particular Brinell hardness testing, and applied if kind of a spherical ball is applied for indentation of the on the surface of the component and load is applied. So, if you just quickly see the spherical ball's diameter if d, then certainly you can measure you apply a kind of load, and the applied load usually varies from 1 kilogram force to 3000 kilogram force depending on the kind of material you are using. So, softer the material, lower is the load you apply, and your indentation diameter may vary from 1 millimeter to 10 millimeter, again depending on the material which you are using. Based on that, indentation diameter will also change. So, usually tungsten carbide ball is used as indenter. So, as you go on applying load, usually there is indentation on the surface and you measure the indentation diameter. So, indentation diameter you can measure in both axes. This is a 2-dimensional view. If you see the 3-dimensional view, this indentation is actually like a spherical indentation. So, where you have, depending on the, if the material is homogeneous in nature, then it is perfectly sphere if you see the top view of the indentation, but if the material is asymmetrical, there is a texture or it is not homogeneous in nature, if it is having properties anisotropy, if it is anisotropic, then naturally you will see that exactly the indentation may not be spherical in shape, its shape may also vary. So, what you have to do, you have to measure the diameter in both the horizontal as well as vertical transverse direction, in longitudinal and transverse direction, and take the average of the diameter, and Brinell's hardness number is equal to 0.102 into 2 into gram force. So, whatever you are applying by pi d square within bracket 1 minus this formula you can apply for the measurement of the Brinell hardness number actually. So, you will find that this particular indenter is tungsten carbide indenter, but you can also use steel indenter. For softer material you use steel indenter. So, Brinell hardness testing unit is particularly applied for the measurement of the hardness of the material, may be softer or may be harder in nature, and its depth of penetration is quite high. So, usually it is used for the actually bulk hardness, or maybe where the surface or maybe surface deposited layer where deposited thickness is quite high. In that case only you can use the Brinell hardness testing. So, you can say it is not really under micro hardness category, but here you can measure the macro hardness of the component. So, if you see the Brinell hardness number, so it is it may be, if you just quickly go through different materials and its hardness value under the Brinell hardness number, this is hardness of softwood, it is 1.6 HBS, S is nothing but it stands for steel indenter. Then if you take hardwood, it is having the Brinell hardness value of 2.6 to 7 HBS. If you take lead, its Brinell hardness value is 5 HB, pure aluminium 15 HB, pure copper 35 HB, then mild steel 120 HB, and 304 stainless steel 200 HB, and glass it is 1550 HB. So, this is basically a kind of, you can say that there is no difference in scale, scale is same, and certainly in one case you can use steel indenter where the materials are softer, and where the materials are very hard, there you can use tungsten carbide as indenter. So, this process is very slow and can be used usually for the hardness measurement of the component. Now, second hardness testing unit usually which is applied for hardness measurement is the Rockwell superficial hardness test or Rockwell bulk hardness test. Superficial hardness test, you say whenever it is basically superficial, it is taking the hardness of the surface, and whenever it is taking the hardness of the bulk, you call it Rockwell bulk hardness testing. So, here you can apply different loads like 15 kilogram force to 45 kilogram force may be applied, and either the indenter may be that typical diamond triangular diamond pyramidal in nature with the cone diameter, cone angle of 120 degree, or it can also be spherical in nature having 1/16 inch diameter of the ball. Now, if you just quickly go through this testing looks like that. So, what you do is that initially the standard is ASTM E18. So, initially you apply very low minor load, and then you just apply very high major load, and finally you release the load and find out the minor load remains, and whatever release is the relaxation is there, you just have try to find out, and from the relaxation you can get the information about the hardness value. For example, this is the case where the particular measurement, this is here actually hardness value is presented in the form of a number. So, hardness Rockwell C, Rockwell B, Rockwell. So, different numbers are there. For example, this is the case where the way it is measured is shown here. So, this is that typical conical indenter. So, here minor load is, for example, it varies from 3 to 10 kilogram force, and then after that, after this minor load, there is setting of the hardness tip with the surface. So, and then you apply major load. So, when you apply major load, the major load varies from typically 15 to 150 kilogram force for the superficial hardness testing, and from 300 to 3000 kilogram force for bulk hardness testing. So, whenever you are applying the major load, so there is permanent deformation of the or permanent penetration of the hardness cone in the deep inside the material, and then after that you release the major load and let minor load remains, and whatever indentation is there, that is actually taken as a permanent indentation or permanent deformation. So, what you do is that you basically measure the hardness testing from that typical release of that load. So, hardness number is nothing but the E is the constant depending on the type of indenter which you are using, minus E whatever is the permanent deformation. So, that gives you information about the hardness number. So, this hardness number again you will see that it varies with material to material. So, usually what happens is that there is always a conversion factor between Brinell and Rockwell hardness scale, but if you just quickly go through the Rockwell hardness scale, you will find that in scale A, in different scale you use different indenter. In scale A you use diamond cone as the indenter, where minor load is usually 10 kilogram force and major load varies. Actually it is it is more or less fixed actually, and then total load again is accordingly the total load changes, and E value will also change. E is a constant, as I mentioned, it depends on the kind of indenter you are using. So, different scales are having, in different scales you use different indenters, different major load, different minor load, and total load is also fixed, and accordingly E value is also fixed. So, if you just quickly go through the material and then subsequently which hardness scale we use, you will be able to understand that in very hard material like cemented carbide, thin steel and shallow case hardened steel, you use A scale. Copper alloy, soft steel, aluminum alloys, malleable iron where hardness is quite low, you use B scale. Similarly, steel, cast iron, case hardened steel and other materials harder than 100 HRB, you use C scale. Similarly, D scale is used for thin steel and you can say medium case hardened steel and paralytic malleable iron. E scale you use for cast iron, aluminum, magnesium alloy. So, you can understand that different scales are there, and for different materials you use different scale, and accordingly here everything is fixed. So, you can apply the major load, minor load and then major load, and then accordingly you measure the E value, and from there you can easily just determine the hardness number of the Rockwell hardness number of that particular material. Now, another type of hardness test which is often used particularly for the surface hardness measurement, that is Vickers hardness test. So, in Vickers hardness test again you can see, if you just see the indenter, it is diamond that pyramid shaped diamond indenter having 136 degree angle. So, your load varies from 1 gram force to 1 kilogram force to 120 kilogram force. So, actually what happens is that here if you talk about this is normal hardness, this particular range is applied, but when you talk about micro Vickers hardness, so their load is even much lower. Here even 100 times lower than that of what you apply in normal hardness testing. So, here the hardness varies from 1 gram force to 1000 gram force micro hardness testing. So, what happens is that here you have to apply the fixed load, and then you have to just keep the that loaded condition for 10 to 15 millisecond or 10 to depending on the kind of material you are using, and then you measure the major diameter and that minor diameter, or maybe diameter in the both sides, or you can say diagonal diameters in both the sides actually, both the axis, and then you take the difference of this diameter, and finally you measure the hardness value, you calculate the hardness value. from this particular formula, that is 1.854 F by d square. But certainly these all are auto calculated. So, Vickers hardness testing is very important testing which can be applied for the hardness testing of the bulk as well as hardness testing of the surface. So, now if you quickly go through the test method for ceramics, like is for advanced ceramics, it is ASTM 1327, CEN 843 for advanced technical ceramics. So, these all standards are applied for different ceramic materials. Here preferred test loads are 9.8 normal and maybe kilogram force is 1, and naturally if you talk about the micro hardness testing, you will find that in micro hardness testing applied load varies from, for example, if you take steel, titanium and these all a little bit harder material, there the applied load varies from 100 to 300 gram force. On the other hand, if you take very low hardness material, like if you take the case for copper, magnesium, those low hardness materials, you take the load which will be varying from 50 to around 25 to 50 gram force, and then accordingly other parameters remain almost same, and you find out the Vickers hardness number, which is perfectly reliable results, and there is no problem of any kind of any kind of fluctuations or maybe any kind of error. So, error is quite minimum when you talk about Vickers hardness testing. Obviously, in Rockwell hardness testing you get the number, so you have to convert it to the absolute value. Obviously, Rockwell hardness testing is also used as standards. So, people often report Rockwell hardness number like RC this thing, hardness of steel is RC, so hardness of the magnesium is RB this thing. So, this is quite often and quite usual practice to say about the Rockwell number, and there is also conversion factor from Rockwell to Brinell and Brinell to Rockwell, or maybe Rockwell to Vickers. But Vickers, if you talk about Brinell hardness testing, there lot of problem is there, a little bit error value is a little higher, because here whenever you just take the photograph, take the impression of the indenter with the help of microscope, you will find that it depends on your observation value. So, there is sometimes some error problem is there, because that is less automated, you have to always measure it, and sometimes while measurement you may find some problem because of the, you can say sometimes what happens is that whenever it is indenting there may be elastic relaxation. So, that is to some extent creates trouble, or otherwise also while observation also you have to be very careful, otherwise you will get erroneous result. Noob hardness testing is another important type of hardness testing, where you use extended pyramid shaped diamond indenter. Again, this is used for surface hardness measurement, this is not used for bulk hardness measurement. So, here load varies from 1 gram force to 1000 gram force, and usually that noob hardness number is calculated using the formula of typical 14.229 into applied load by long diagonal indentation square. So, in the other case you take average, but here you just measure the long diagonal indentation length actually. So, which is important, which gives you the, which is good enough for giving you the hardness number of the noob hardness testing. So, if you just quickly go through the ASTM standard for measurement of hardness of metallic materials, you will see that in Vickers number like ASTM E384 is the standard, or ISO 6507. So, where load range usually from 10 gram force to less than 100 kg force. This is for, obviously this is for normal hardness, and 1 gram force to 1 kg force, this is for typical you can say that surface micro hardness, for micro hardness measurement. Similarly, for noob hardness testing, if you see the value, if again varies from 1 gram force to 1 kg force, and the specifications are ASTM E384 or maybe ISO 4545. If you talk about Brinell hardness test, and again The standards are ASTM E10 or ISO 6506. Its load varies from 1 kgf to 3000 kgf, and Rockwell actually ISO 6508 or ASTM E18. So, here load. So, these all load ranges and standards, these are very important, because whenever you just report the hardness value, in addition to the hardness test you have used, you have to sometimes refer also the ASTM standard, then only people will accept, particularly when you talk about the you are talking about the industry scale property measurement. There you have to always follow the standard, so that they understand the process which you have applied. Now, if you talk about the coating, so whenever we just apply a thin layer of coating on the surface of material, the coating on bond strength is very important. So, we will be discussing about the coating in a later class, but the basic objectives of this particular course is to minimize the surface dependent degradation, or to minimize the attack of the environment, or maybe you can say that to minimize the adverse influence of the interaction of the environment with the component surface. So, for that we apply a barrier layer usually, or sometimes we also apply another layer which suits the environment. So, these two approaches which we usually use. So, in case of barrier layer, for example, the environment consists of lot of corrosive species or lot of other species which are not really good for the surface. So, we apply another layer on the surface which is not really which suits the, which is very much compatible in the environment, so that environment does not react on the surface anymore. For example, see the case for one case it is mild steel, the other case 304 stainless steel. In mild steel, if the environment is highly corrosive, particularly if it contains lot of water or water molecules or other species, then naturally what happens is that there will be reaction of the mild steel with the environment and formation of sulfuric oxide or ferrous oxide layer, and which is highly loose and porous in nature, and hence it is not really good. So, it is there is degradation of the surface in the environment. On the other hand, if you apply very thin coating of stainless steel, or maybe if you replace the mild steel with AISI 304 stainless steel, you will find that the degradation probability is very less, and even though degradation is there, kinetics of the degradation is very low. Or you can also apply a very thin layer of tin coating on the surface of the mild steel. So, steel is having very good resistance to attack against like water. So, steel will tin will remain unaffected. So, you will find that tin acts as a barrier layer, and hence the surface is protected. So, you have different reasons for application of coating. So, whenever you are applying coating, some of the coating techniques like physical vapor deposition, chemical vapor deposition, electro deposition, those coating techniques, if you see the coating deposition, you will find that the coating actually gets deposited on the surface, but there is minimum interaction of the coating with the substrate. So, in that case what happens is that because of very less interaction, the substrate is, or maybe you can say that substrate coating interface is very weak. So, bond strength is one important parameter which needs to be specified whenever you talk about coating. So, different coating techniques actually offer different bond strength. So, you whenever you are interested to apply to measure the bond strength, you have to follow some testing procedure. So, this testing is one of the important testing, that is 4-point bend test, where you can measure the coating, that adhesion of the coating or adhesion strength or bond strength of the coating with the surface. So, here what happens is that on the surface you have the substrate is this is nothing but coated substrate. On the substrate you have a coating, and this particular coated substrate is kept on a kind of vise, and on top of that you apply the force at two different points, and there is a acoustic sensor. So, you go on applying the force, and what happens is that you bend the component. So, whenever you bend the component, naturally you will find that where from the failure starts, you have to note down. If the failure starts at the interface, then you can say that or maybe the load at which failure starts at the interface, that load can be accepted as the adhesion strength of the coating. The failure may start on the surface, failure may start at the coating, failure may start at the interface. So, it is very important that you note down where from the failure is starting. So, like for example, it is the kind of surface coating and the component is subjected to bending. So, you will find that in one case you will see that the coating remains, coating remains and then substrate gets bent. So, there is a failure of the coating, detachment of the coating. Other case you see that there is no detachment of the coating. So, in this case you can say that it is highly bonded to the substrate, but here it is weak adhesion, not really bonded to the substrate. So, this is a kind of qualitative measurement. If you would like to specifically mention the bond strength by the application of this coating technique, so you have to go on applying load in a you have to go on increasing the load or maybe load for bending in a periodic fashion and find out the load at which the coating fails. So, that load may be accepted as the adhesion strength of the coating, or failure you can say that bond strength of the, or the load below which up to which it is stable can be accepted as the bond strength of the coating. Now, if you just quickly go through the indentation testing, there is another way by which you can qualify the coating, that is called indentation testing. So, when you do indentation testing, there may be elastic failure, plastic failure, or failure after penetration of the indenter inside the substrate. So, from there you can also get information about the kind of failure has occurred on the surface. So, this is a little bit the testing is a little bit different. So, it gives you information about the, you can say that there is a wear term which we are acquainted with in the past, that is indentation wear. So, this particular indentation test gives you information about the resistance to the indentation wear. So, indentation wear, if it is due to indentation testing, if there is elastic failure, naturally you will find that there is delamination of the component even in elastic range. If it is plastic failure, you will find that there would be subsequent plastic deformation and failure, and if there is penetration of the indenter without any kind of failure, you can say that this is having very good resistance to the indentation you can say. So, there is another kind of test which is also applied for measurement of the bond strength, that is pressurized blister testing. So, here in the substrate, this is the coated substrate. So, here from the back side of the substrate you can have a very thin delamination or very thin, you can say that that micro crack formation, and you go on applying the you can go on applying the either water or maybe air at a very high speed. So, you can see it as pressurized blister. So, you blister it with a very high pressure and find out the delamination radius. So, from the delamination radius you can understand the how is the coating strength. So, what is the blistering height. So, this is again a kind of standard testing. So, these are all quality testing, you get quality result, but you do not really get, maybe you can get you have to specify the pressure at which there is delamination, or maybe what is the radius of delamination, how is it varying with applied pressure. So, now if you go to the typical another testing for the for knowing the adherence of the coating, that is scratch testing. So, in scratch testing what you do is that you basically go on scratching the surface and subsequently you measure the coefficient of friction as a function of time. So, you will find that whenever you are measuring the coefficient of friction as a function of time while doing scratch testing, you will find that coefficient of friction actually whenever it is on the coating side, you will find that it is having some coefficient of friction, and as you go on applying load you will find that coefficient of friction will also change. So, from the point of the deflection of the coefficient of friction, you can understand that there is failure of the coating. So, this is very important way of determining the adherence strength of the coating, because you will find that as you go on increasing the load while scratching the component, in scratch test one important information what you get is the first of all the depth of scratching, second information what you get is the coefficient of friction. So, coefficient of friction usually is taken as a measure for knowing the quality of the coating. So, usually you get information either the coating is highly very low coefficient friction or very high coefficient of friction. Usually there is always difference in the coefficient of friction of the coating and also substrate. So, at a point where the interface reaches, you will see that the particular coefficient of friction value changes from coating value to the substrate value. So, that particular point is taken as the load at which the failure of the coating occurs. So, scratch test is also very important test for knowing the adherence strength, adhesion test or maybe bond strength of the coating. So, this is a similar scratch testing is shown at a very high magnification. So, it is the scratch testing apparatus. So, where is the force and vibration measurement is there. So, you will find that coating after as you go on scratching, you will find that there is in one case there is a coating left on the surface, and other case due to strong coating adhesion strength there is plastic deformation of the surface and also minimum detachment. So, you can say it is having very high. So, from observation of the cross section of the coating, you can understand the how strong is the coating is. For example, this is for if you see this coating, you will find that while doing scratch testing, this is not really the real surface, this is cross section of the scratch tested component. So, you will find that here that there is a lamination of the coating. So, you can understand that there is very weak adhesion, but here the adhesion is very strong. So, from the observation of the cross section also or interface also, you can say you can get lot of information about the quality of the coating. So, if you talk about coefficient of friction, naturally it is not only the it is not only a kind of parameter which is dependent on the composition, it also depends on the hardness of the coating, thickness of the coating, then surface roughness, debris. So, many parameters are there which determine the coefficient of friction, or maybe you can say that the rate of wear, because rate of wear or wear volume which is lost because of wear is also dependent on the coefficient of friction. So, now these all testing techniques we will be discussing in the next class. Thank you so much. So, in this particular talk we discussed about particularly hardness testing and also the coating adhesion testing techniques. So, now we will be discussing about different tests which are applied for just measurement of wear resistance and also measurement of fatigue property of any component. Thank you very much.